So in this video, we discuss about the practical differentiator circuit. So compared to the ideal differentiator circuit, you can see I have added R1 and CF capacitors, right? So this R1 is added with in series with C1 in order to avoid the poor signal to noise ratio, and CF is added in parallel with RF to minimize the noise and improve the stability and reduces problem due to the input impedance. So let us now discuss applying the KCL at this node. Okay. KCL at this point, I can write input current is equal to outgoing current. So IC is equal to I1 plus I2. So I is nothing but V by R. So this is Vi minus 0. The current is flowing from Vi to 0 because this voltage is 0. So this is 0. So Vi minus 0 divided by resistance impedance. So that is R1 plus 1 divided by SC. Okay. That is equal to what is I1? I1 is 0, 0 minus V0 divided by 1 divided by CF plus 0 minus V0 divided by RF by comparing this one, I2. Okay. So on solving, I will get VA into SC1 divided by R1 C1 S plus 1 is equal to minus V0 SCF minus V0 divided by RF. So if I take the V0 common, I will get this equation. So since it is in the Laplace transform, so V0 of S divided by VA of S is equal to minus SC1 divided by 1 plus SC1 R1 divided by plus CF RF plus 1 divided by RF. So rearranging the equation, I will get minus S C1 RF divided by 1 plus S E1 R1 into 1 plus S CF RF. Okay. So for RF CF is equal to R1 C1, I can write this is equal to minus SC1 RF divided by 1 plus SC1 R1 the whole square. So we know that S is equal to J omega, right? So V0 of J omega divided by VA of J omega is equal to minus J omega C1 RF divided by 1 plus J omega C1 R1 the whole square. So omega is equal to 2 pi F. So if I substitute, I will get minus J 2 pi F C1 RF divided by 1 plus J 2 pi F C1 R1 the whole square. So this equation I am writing it as so instead of instead of 2 pi C1 R1, I am writing it as VB the whole square FP. Sorry, FP is equal to 1 divided by 2 pi R1 C1, or else I can write it as 1 divided by 2 pi RF CF, right? Both are same. So you can see the ideal opamp. The ideal opamp is increasing at the rate of, this is my ideal differentiator, right? Ideal differentiator. So here you can see it is increasing at the rate of plus 20 dB, right? And FA is nothing but 1 divided by 2 pi RF C1. This is the ideal differentiator. So for the practical differentiator, so this is my uh, so this is nothing but the ideal differentiator, right? Ideal differentiator increasing at 20 dB rate. Okay, and this is nothing but your FA, right? And now this FP is somewhere here. Okay, so the FP is somewhere here. So I can write this FA is less than FP. Okay, so I have to design it like that. Okay, so till this F which is less than FP, the gain get increased at the rate of plus 20 dB. Okay, and so after this FP, okay, so after this FP, after this FP, the gain get decreased at the rate of minus 40 dB, right? Sorry, yes, this so after this FB, it is falling at the rate of minus 40 because this is 20 dB. So if I minus this 20 dB means the gain is like this. Okay, if I again reduce it by minus 20 dB, the gain get reduced like this. So this is nothing but your response of the practical differentiator. Okay, so this 40 dB change. Okay, this 40 dB change is due to that is F which is greater than the FP. Okay, this 40 dB change per decade in gain is due to R1C1 and RFCF. Okay, so you can see in uh, the ideal differentiator, if I increases the frequency, uh, there it will causes it will amplify the noise and it will causes a stability problem, right? But here uh, since the gain is reduced at high frequency significantly, it will avoid the high frequency noise and stability problem. Okay, so since the gain at high frequency is reduced significantly, thereby it will avoid the uh, stability and high frequency noise. So I can write this FA is less than FP, which is less than FC, where FC is nothing but a unity gain bandwidth of opera in open loop configuration. Okay, so for the good differentiation, T must be greater than or equal to R of C1. So this is the condition. Okay, or I can write this R of C1 is greater than R of CF or R1 C1. Okay. So the question is design an opamp differentiator that will differentiate an input signal for FA is equal to 100 Hz and FP is equal to 1 kHz. The second question is draw the output waveform for a sine wave of 1 volt peak at 100 Hz applied to the differentiator. Repeat it for a square wave input. So, uh, so this is the circuit which I am going to give. Okay. So for this one, if you see R1 C1 is equal to R of CF, so that I have put the resistance like this, and I know the value of FA, right? What is what is the formula for FA? FA is equal to 1 divided by 2 pi from the ideal differentiator. FA is equal to 1 divided by 2 pi R of C1. So therefore, I can write FA is equal to 1 divided by 2 pi R of C1, that is equal to 100. They have given how to design FA is equal to 100 Hz. So if I take the value of RF is equal to 15K, 15.9K. So if I assume, or if I assume, C1 is equal to 0.1 microfarad, okay, you substitute here. So you will get RF is equal to 1 divided by 2 pi 0.1 into 10 power minus 6 into 100. So you will get the RF value is equal to 15.9K. So taken RF is equal to 15 into 10 power 3. Okay. So we know FP. What is FP formula? FP here is 1000, that is nothing but 2 pi R1 C1. Right. So C1 value also I know already. Right. So if I substitute R1 1 divided by 2 pi into 10 power 3 into 0.1 into 10 power minus 6, I will get R1 value is equal to 1.59K. Okay. So since we know that R1 C1 is equal to RF CF, so in order to find the value of CF, right? So R1 C1 divided by RF, I will get the value of CF, that is equal to 0.01 microfarad. Okay, so you substitute that value. Okay, so for the second problem, okay, so for the second problem, draw the output waveform for the 1 volt peak at 100 Hz as input signal is applied to a differentiator. So what is my input? Input is 1 sine 2 pi into 100 T. So this is the input voltage that I am giving to a differentiator. So we know that V0 by VA is equal to, from the ideal differentiator. So what is V0 by VA? V0 by VA is equal to, let's see, okay, so V0 by VA is equal to minus R of C1 j omega, right? So I can write V0 by VA is equal to minus j omega R of C1. right? So I can write V naught is equal to minus R of C1 minus j omega, sorry, j omega VA. This j omega VA, I can write it as yes, right? So this is nothing but C1 d of Vi by dt. Okay. This j omega, I can also write it in terms of time domain. I can write it like this. So you substitute the value of RF. So what is RF? RF is 15K, 15K, right? What is C1? C1 is nothing but 0.1 into 10 power minus 6 d divided by dt. What is input? 2 pi into 100 t. So if I differentiate, I can write minus 1.5 into 10 power minus c. So if I differentiate, I will get 2 pi into 100 cos 2 pi into 100 t. So on solving this one, 2 is nothing but minus 3 into 10 power minus 1 into pi cos of 2 pi 100 t. So this is nothing but so on solving this one, you get 3 pi minus 0.942 cos of 200 pi t. Okay, so this is approximately equal to minus cos of 200 pi t. So now let us discuss the third problem. So for the given problem is for the square wave input, right? So for the square wave input, this is of 1 millisecond. Okay, I will get the output like this. Okay, this is my output, and the frequency is same. This is 1 millisecond, and this value is nothing but V saturation value, and this is nothing but minus V saturation. Okay, so we will discuss this problem in the practical manner also. Thank you.